mesh controls that you can do to make unstructured mesh a little bit cleaner. Beyond that, there is structured grid, which is just like everything is a perfect cube or at least some sort of rectangular prism. Sometimes they're a little longer than others. But the absolutely ideal would be to have everything being a complete structured grid. That is not always possible, though. There are some ideas for mesh quality, such as orthogonality, skewness, relative size, and aspect ratio. The gist of it is you don't want too many abrupt changes in your cells. So even if you're increasing in cell size, you don't want one cell to be here and then your next cell to be like this, because then what about all the data here and here? That it's not going to transfer well. But say you need it to be this big, you slowly, this is exaggerated still, but you slowly increase over time. You want to, even if you do want to morph and change it so it's not a perfect square, you want to slowly morph and change them across the surfaces or the volumes in the case. Slow changes are always better than sharp ones. Boundary layer, if you're dealing with boundary layers, sometimes you might not be. It is important to calculate the height of the first cell required. That is called a Y plus calculator. We did that for you last time. If you want, on day 3 or so, we can show you how to do that. It's a little complicated, but there's some online tools you can use for it. Essentially, you don't want if the cell height near your boundary layer is larger than the size of your boundary layer, it won't calculate that boundary layer because it's too big for it. It needs to be as big or smaller than that. Yeah. Yeah, this inflation layer. Inflation layer is a type of mesh control that you can use to make sure that the proper cell height is the cell height you need for your boundary layer.
All right. And so that was kind of everything we covered day 1, and then we created a mesh, but we don't need to go.
Yeah, we don't need to go into too much detail.
So starting with day 3, the first thing we're going to talk about is...
Day 2.
Oh, yeah. So the first thing we're going to talk about is turbulence models. And this is what is used to kind of capture all like the differences in the flow. Well, turbulence. So the flow is not linear. You're going to need one of these. And that's most flows, definitely for aircraft, are going to need a turbulence. So that is this is what's going to pretty much the only thing you're going to use for most of the time is INS, and that's Reynolds average Navier-Stokes simulation. So that's what most of the CFD is. And this one is the easiest to solve, and it gives you a time average, and it gives you a sufficient level of accuracy when you're only looking at at the aircraft as a whole. Like if you're trying to find the whole lift or the complete drag component, then it gives you sufficient accuracy. But if you're trying to look at small level flows in the boundary layer, you need something more precise. And that's where LES and DNS comes in. These are different from them because, so you have to have a much finer mesh. The mesh has to actually, it has to be a quarter the size of the smallest vortex. And so that can get into mesh counts of tens and 20 million. And these, they won't be really used in industry, maybe LES. And LES can be combined with INS to give you some more accuracy, but still less expensive. But DNS will never really be used in industry. It takes too long. You do see it sometimes in research when they're looking at really complicated flows, but these can take months to run. So you guys probably won't be using this for your competition teams.
Yeah. Yeah. So last class, we kind of just went over the geometry and the meshing. Now we're dealing into the actual setting up the model. Like how Dr. Sharma discussed, the Navier-Stokes equation, that is the governing equation for everything. The next step of setting up and solving the simulation is a software version of what you would do in like your heat transfer class or your flow dynamics class, where you would choose what assumptions are okay and not okay to make, what boundary conditions are pertinent to you, and what are your initial conditions. Also, the computer can set up and solve the equation for you. Knowing what boundary conditions to use, what assumptions are okay, and what your initial conditions should be the most easy thing to understand because that's what you're designing around. Is your aircraft going 60 meters per second or Mach 5? You should probably know that. But the more complicated stuff is the boundary conditions and the assumptions to make. And some of that does come with experience. Some of it comes with just copying research papers and being like, hey, this paper is doing stuff with a helicopter blade, and we're an RCT and ARCT, and we're also trying to make a little helicopter blade run. And they're using these assumptions. Use those assumptions. See if it works for you. If not, sometimes it comes with experience.
All right. So now we're gonna move into Fluent. So if you want to open, so we can open a workbench.
Did you share the
Yeah.
Some files.
Right now just open workbench, but you can download generic aircraft.mesh. And that will be the mesh we're gonna be using.
It should be in the KSU OneDrive.
Yeah. Everyone was here last time and get that folder shared with them, right? Great.
Everybody?
You get it?
There you go. Making sure I can read all your chicken scratch. I think I can. One of you writes real tiny.
Hmm.
You?
Yeah, I don't know his name.
Matthew Woodbine?
I know, right? That's
You write about half the size of a single square. Is it equation size? Bro, you realize like all the professors here are really old.
I mean, they can't read it, can't give you back.
He's thinking ahead back there.
Okay, do 'em.
They can't read your test, they can't grade your test.
Generic aircraft.mesh. So now we should have workbench open up, and you're gonna pull out actually we can go down to component systems and pull out a Fluent, just a Fluent. And then here,
Slow
well,
down, wait till everybody got it. Is everybody here? No. Oh. Okay. You need help? If you're on it, let's say, exit out and open it again. I think you might have opened it.
all right, so is everyone else got this on the screen? Right? So we'll go to setup. You right click on that, and you have this screen pop. Oh, my legs. Okay. So and then you click edit again. And the Fluent launcher should pop up. So you have a couple options, 2D and 3D. We're doing 3D, so make sure that's selected. Select double precision. And then solver processes. So that's, if you guys remember from last week, that's how many cores you're gonna use. Did you guys use 12 last time? But okay. So yeah, you guys can use 12 again. I use 12 too because I'm a mode accessing.
Hey, Andrew, you seen
see that open where it doesn't open any of the other,
Are you, is it the right, if you open up, is this 2024?
yeah, it's 2024, it's R2 and everything. It's just not opening up the file, just like,
Just open it up.
oh, yeah, you
That's
can
what I was
just,
like.
so close, Workbench and just go through it. There you go.
Yeah, and that same module will pop up again. So now that we're here, click double precision, 3D, and then 12 solvers. And we're gonna go click, start.
Yeah?
Yeah. I'm remote accessing that computer.
Also.
I got like 30.
Yeah, on the lab. Lab.
Downloaded more course?
Yeah. I downloaded more RAM off the internet.
Wait, I do that. I gotta do that in my computer.
Alright, so does everyone have Fluent open now? To look like this?
You do?
Yeah,
Was it 2D?
3D. So. Well, wait, let me get it up. Alright, is everyone good?
You got it?
Yeah.
Okay.
Why are you
Doesn't sound
saying
too
it like that?
confident.
Oh, no.
Okay, so we're gonna go to File, Import, and then you have Mesh here. So click on Mesh.
Remember to slow your mouse because the screen likes to jump.
Alright, so you guys have like your file directory open up. So find that file wherever you put it. Yeah, and it's that generic aircraft mesh on the OneDrive. Download it to your computer before uploading it, and then just upload it right here. So, click on this.
Yeah, file
it should
import
load in.
and then find your file.
Oh, it's, yeah.
Yeah, you have some stuff in the console. If the stuff coming up, that means it's probably
The
working.
council?
Console. How do you say that?
The council.
The council.
Console.
The council.
The council on the computer has.
Alright, and then you guys should see your blue sphere pop back up that we were doing last workshop.
Everybody got the blue sphere?
It's the mesh. So it's that mesh we created last time. Did you ask what it's? Did you ask what it's for?
No, just like what you.
Oh yeah, mesh. So file, import, and then mesh.
Yeah, it's gonna look
Yeah,
when you first import it, it's gonna look like the geometry. You can change the view in like
so now we should have
view
this.
to
And if you-
show the mesh.
This is a pretty cool feature. Oh. Display mesh. If you click this little, I don't even know what you'd call that.
It's like a little globe.
Yeah, a little like triangular globe.
Yeah.
You get this screen, and here, so if you select edges, then you see the edges of the mesh. So you see all this. Nodes will kind of look crazy, but
Slow your button clicking, man.
I'm just showing the feature.
I know, no, the screen can't keep up with you.
Yeah, it is. Alright, and then you can also select what you want to see. So let's say you just want to see the wing, then you can so if you go up here, you can deselect everything with this X button. Deselect, and then you can just select wing, and then now you can see just the wing. And you can do that for everything else. So if you like need to check something for some reason, like if you wanted to check the mesh again on here, now you can actually see it.
Mhm.
Anybody
need any help so far? Looks like we're doing good.
Alright. Yeah, I don't know how to do it with the Teams call.
Oh,
Is there a way to full screen the screen you're showing?
you should be able to hit share.
I am sharing the screen. This is coming from my laptop, but remember the HDMI cord doesn't work.
Oh,
But I don't know if there's a
just full screen your Fluent.
my Fluent is full screen. It's because it's on. This is a Teams call.
Oh, it is.
Oh, wait here.
It's auto transcribing our voices in
Yeah,
the
yeah,
chat.
yeah. It's a Teams.
Yeah, we got.
Yeah.
I did not know that that was happening. Good to know.
Everything you say is recorded. Well, I guess it actually gets blamed on me. Everything that's said in here is transcribed under my names.
So we're all in the clean. Yeah.
I had an error.
Did you download it? Did you try to open it from OneDrive or did you download
And
it
hide
onto
the
your computer
transcript. That makes it
first?
like,
I downloaded it on.
Okay.
Well, I like the transcript. It was talking about it had errors for 5 years.
I don't know how to hide this over here. This should be a way to full screen.
Go
It's
back.
after the qual. Is this big enough? Okay, close this. Does that look better?
What's the
So I can't figure out how to give it. I don't know if there's a way. Does anyone know a way on Teams or like full screen?
What's the name of
something?
the exact file? By the way?
It's generic aircraft mesh dot mesh dot msh.
Like that 5. There's a 5.
Oh, it's H5. That's something to do with Fluent. Alright. So is everyone else on the screen?
Not yet. He had a fatal flaw in Fluent.
Fatal?
Yeah, it came up and said fatal flaw in the crash.
I guess
Yeah,
just try
open Fluent,
opening
right.
it. Close.
But if you're doing this, close out a workbench or else it'll interact with each other.
Alright, so
Don't say it.
and then if you go to general under setup, so it's kind of the same as the meshing process. We kind of run through these steps. So general, and then this screen should pop up. So our solver type is going to be,
They can't see.
Yeah, we can't see the wire.
what the hell? It's zoomed all the way out. I don't know why you can't see my full screen. I can see it on my,
We're good now.
oh yeah.
So import.
So if you put general, then this screen should pop up and it comes up on default anyway. So you have solver and our type is going to be pressure based. So it's going to be defined by pressure. You would do density based, mainly for like supersonic or hypersonic flows where the density is changing a lot. You need a density based solver. And we'll keep our time as steady state instead of transient.
Andrew, okay. What was the first step? It was import, then what?
File, import mesh.
That he does not have that option on here. I cannot do that.
What? That's weird. Very fresh. If you can cover over the CG, that one. Okay.
Mesh and data?
Just move.
Did you complete teaching with them?
Yeah, this one says.
Yeah, it's a bit different.
Download the
Yes.
CG version of it.
It's not recognized my file type. You can
Do all files and see if it works. And I don't know. Okay, so we have our general settings defined.
No.
Yeah.
Yeah, some errors before.
So how did you try opening the, check if he has just Fluent.
Yeah, we have just.
Why does, it says Fluent teacher. Is there another Fluent installed on it?
Like that's. The what? Please let me exit. I did not have. Gravity. Check gravity. In order to open,
No gravity.
you need to-
We don't mess with gravity. So yeah, that's kind of the weird thing. I guess gravity is not really needed in 2D. I guess, I mean, in like aircraft flows. I don't know why, because obviously there's gravity on Earth, but I guess it doesn't.
What is the name?
I think you use it more like on, like if you're like simulating like wind through buildings or like through pipes where like the gravity will pull it down. Maybe for like water flows.
So would enabling gravity like pull the flow down?
Yeah, it would give it like an acceleration downwards, but
It's also so most of the time.
well, air doesn't get pulled down. Oh, because there's air below the other air.
Well,
It's all,
so most of the time,
Air's not
the
getting pulled
effect of
down.
gravity on the flow is very minuscule. It's when it comes to like the actual speed of the aircraft. gravity itself as a force is very weak. So if you're going if you're not like a very slow little glider, it's probably not going to affect the flow of your airplane that much. If you're moving at any relative speed that most planes move, yeah, it's not going to affect you very much.
Yeah, and also air is not very dense. Yeah. So air is not very dense, so it doesn't have a lot of mass. If you were like simulating water over like a waterfall or something, you probably want gravity enabled, or the water will just keep going.
I mean, it's like glider because it's moving slow, but like
It wouldn't though.
it's a very
I don't
minor
know.
effect. If you're doing a good jumping over most aircraft, probably won't need it. But if you're doing like for some instances, if you don't want to do the flow over the entire aircraft, but you're more so interested in like the minute details of like, yeah, but I'm trying to add a winglet right here, and I'm trying to change the angle of the winglet, and you only are simulating a small section of the aircraft, then it might come into play more because you're going into more small details, and gravity is a small detail. Besides that, though, generally not going to use.
Yeah.
It's mainly because the force of gravity is denoted by like being times rho as well in fluid mechanics. So you need like the density of the fluid that you're in to see how big of a force gravity is going to have on that helmet.
Yeah,
I got like 2 years to put that. I'm taking it right now.
Alright, so
You close?
now we can go down to models and we can click this arrow and this will open up all of our models. So there's a bunch of different things you can do in Fluent. You can do multi-phase, which would be like different types of flow. They have like a species if you wanted to like simulate, like they can do like chemistry basically, where it simulates chemicals reacting with each other. Heat exchanger if you have like heating in an aircraft and you want to simulate it cooling down. And then energy is a big one. This is used when you have compressible flow and there's like energy in the air, and you would turn that on if you're above Mach 0.3. And then viscous is our turbulence model. So we'll double click viscous, and it's default set to K omega, which is a commonly used one. But for traditionally for aircrafts, Spotlight or Mars is better, and it's faster. It's a one equation model instead of two equation. So it runs a lot quicker, and it's also better at predicting flow of airfoils. K epsilon, K omega are more accurate in like internal flows, and then also, I mean, flows of an aircraft that aren't like airfoil. And then you can see here we have our DES and LES. That's what we talked about first. Those you need a very fine mesh, and they'll take a long time to run, but they give you better accuracy.
Do you use DES or LES for your research?
I've used DES a couple of times, but not for the. But all right. So, and we're gonna leave energy off because we're doing incompressible. So now we can close models, and we'll move on to materials. We don't actually need to change anything, but I'll show you guys. So you can define what the fluid is. So it's auto-defined as air, but you can also change, like, let's say you want to simulate at high altitude. You can change the density of the air, and then that will simulate at a high altitude. Let's say you want to simulate on Mars. You can change the air to match the properties of Mars, or you can do any other type of fluid like water and other types of gases. But we're going to leave density as constant for now. If we were doing compressible flow, we'd use ideal gas, and that's it's a certain type of equation that defines how density changes, and we'll leave viscosity also as constant. And then we can also change aluminum is what it's default at, and it doesn't really affect it because we're doing no shear. But if you were trying to simulate an aircraft and you want to like define the material, you can do that here. Done with that. Cell zone conditions, we don't need to do that. So yeah. In the model, or the viscosity, or the material. Oh yeah, we changed it to a Spotlight or Mars from K omega. Does everyone have a viscous Spotlight or Mars? Great.
Spolar MR is the most commonly used viscous model for aircraft simulation. I've even gone over like NASA papers, and NASA still uses Spolar MRs.
Yeah, and especially like in industry, they'll use that because it's simple because you don't have months to do a simulation. They have deadlines they gotta hit. But so now we'll go to boundary condition. You click down, and then you have inlet. So this is where we define our inlet, and we're gonna click on it. Well, actually, first, double click on boundary condition itself, and you get this screen pops up. And we're not actually going to use a far field. A far field is something you would use in compressible flow, and you just define the pressure at the outlet, and it will flow through. But it won't work since we're doing incompressible. It'll give us an error. So we're going to select far field, go down here, and go down to type. I'm going to click down, and you get this little menu, and you scroll down to velocity inlet. It's down at the bottom. We'll select that. So instead of defining the pressure at the inlet, we're going to define the velocity. And then this screen should pop up, and we'll define the velocity magnitude. And also set, so this top thing, we're going to set it to magnitude and direction.
Yeah, so right now
we need to define where the flow is going.
Yeah, exactly. So right now, our can you zoom out again so you can see the actual dome? Our dome is, well, it's a dome. So, and the entire thing is labeled as kind of inlet. So if we did the default settings, which was velocity, magnitude, normal to, it would set the air as going normal to every point on the dome, coming from all different directions. It's not what we want. We want to define a direction in respect to our axis, not in respect to being normal to the dome.
Yeah, because then you just have flow coming from every direction. If you were doing a rectangular domain and you just had the front face as your domain, you could do normal because it will just go straight.
Because
But
then it'll just be at the front edge of the front face of the.
I like to do components just to be safe, to make sure the flow is going in the right direction. So you can see our aircraft is orientated this way. So the front is this. So we want the flow coming in the X direction. So we'll go down to components, and we'll define it as a 1 in the X component. Let's say if we wanted it go in the other direction, then we do -1, and that will go down the negative X axis. And then you can also define, if you wanted the flow coming in at like 10 degrees to simulate an angle of attack, you can do, so it would be cosine 10 degrees would be your X component, and sine 10 degrees will be your Y component. That just comes from.
Can you put in like actually cosine? Will it work
I
that,
don't
or do you have to
believe
put,
I don't believe it will.
do you have to put an actual number that?
Yeah, no, it doesn't let you use any letters.
Oh,
You
it's-
can use a little hand calculator.
Yeah, so I mean, you could just do it on your calculator real quick, and I can't type.
So when you're doing angles of attack, you don't need to create a separate model for everything. You can just have the plane will be horizontal, and you'll be determining the angle of the air itself instead of the angle of the aircraft. Question?
When you say angle of attack, are you saying like you're pushing the whole aircraft up?
So yeah, angle of attack. So if this is the aircraft, and like the wings are out this way. Angle of attack is the actual like.
Like if you wanted to like.
On the wing, but not the aircraft.
Yeah, you would have to have a new model because, I mean, you can't change, if you change the components of the air, it will affect the whole aircraft. So if you want to do like the wing incidence, then you could like rotate the wings up a couple of degrees and leave the fuselage. But yeah, wing incidence is when you have the wing at a couple of degrees high or low.
The incident of the wing is basically installing the wing onto the aircraft already at an angle of attack. So even though the aircraft itself is flat, the wings are already angled up. That's called the wing incident. Some aircraft have them. Some, like most modern wings, they're very complex geometries where like they won't have an incident right at the aircraft root, but as the wing goes out, it'll actually twist either up or down, to create an incident at different parts of the wing. Wing geometry can get very complicated if you want to get really nuanced into it.
So yeah, a lot of aircraft, like if you have ever seen like a Cessna 172, they have a couple degrees of incidence to help them take off in a shorter distance. And then the wing twist is so if you have the root, typically you have the root at a high angle and the tip at the low angle.
Yeah.
So since this is at a high angle, it will stall first because it will be at a high angle of attack than the root. So you get the stall here first. You can still control the aircraft because your ailerons are out at the tip. So you still have control of the aircraft. If it's stalled there first, you lose control of the aircraft and spin, and that's where a lot of the crashes from like World War II came from that.
Yeah, a little fun fact about the World War Spitfire. It had a perfectly elliptical wing, which gave it like nearly mathematically perfect lift over the entire wing. The problem is, due to being mathematically perfect, it had no twist in it or anything. So when the wing stalled, the entire wing stalled at the exact same time. There was no warning. So the World War II pilots would just be flying, and oh no, I pulled up a little too hard. Your plane drops out of the air immediately.
Okay.
They don't want that nowadays. They twist the planes here and there to make it so like, oh, I feel a little turbulence on this side of the wing or that. I need to pull out of that so that I don't stall my whole aircraft. They didn't know that back in the day, and a lot of people died falling out of the air.
All right, so now defining the inlet, we'll go back to our case page and we'll see the airspeed we want to define it at. So we're doing 160 miles per hour because that's the landing speed of a commercial aircraft. So, but we need to do it in meters per second. So 71.5264, and we'll go back to our inlet and we'll define that 71.5264. So now we have our velocity defined. Your supersonic and initial gauge pressure, you don't need to set that for this low speed. You don't really technically need to ever set it, but at higher speeds, you want to set it and it will make your solution faster. And there's calculations online that tell you how to do that. Yeah, press apply.
Yeah.
Press apply and then you can close it. So then we can leave internal. So since we named our faces earlier, it auto defines stuff. So it knows like what we want as our internals, what we want as our symmetry face, and what we want as our walls. So we have our fuselage, our wings as walls. And these are set as no slip walls. So they don't have any shear forces acting on the flow. And that's how we want it.
So this is earlier in the last workshop when we talked about naming the different surfaces of your geometry. This is where that comes in. If you name something wing or fuselage, Ansys will actually know what that means and assign it a setting of a wall, a certain amount. If you assign something to be fluid or inlet, it also knows what that means and it'll accordingly do so. So you can just make up funny names for it, but if you want to be quicker with your simulations, I recommend keeping to a standard practice of doing far field, inlet, outlet, if you have those in your model. Naming wing a wing, that way Ansys just speeds up and knows what you want to do without you having to input those for it.
So in the next, we can skip all this stuff. This would be stuff you would define if you wanted a moving mesh, but you don't want that today. So we'll go down to reference values. And these are the values used in the calc. Oh, you got a question?
Yeah. So, and I forgot.
So they have
Oh,
something to do with
right.
moving
All right.
methods.
Yeah, you can come back to it if
Yeah,
you
it
remember.
was earlier with the boundary condition. I forgot what it was.
All right. So we got our reference values, and these are what's going to be used to for Fluent to do calculations. So if it's doing the coefficient of lift, this is what area it will use, what length, what density, and stuff like that. So it auto sets the density correctly, the temperature.
I remember. So the dome, do you name it far field or do you name it velocity inlet?
It kind of just depends on what you're doing. I think if you define it, yeah, if you want a velocity inlet, you could define it as velocity inlet. So we'll do compute, but so get these values to do it quickly. You can do compute from far field, and that will compute it from the inlet. So that will give you your, as you can see. Oh wait, I clicked the wrong one. Click on far field, and that will compute these values from the far field. So you get your velocity, you get your heat at the inlet, and that's what you want. Stuff you're gonna have to define yourself is the area, and we're gonna use the wing area for this because that is what will be used in the coefficient of lift calculation. So 0.0494 will be our wing area.
So one thing I will say is that if you wanted to do it at higher altitudes or varying different altitudes, this is where you would go in and change the temperature and everything for the different altitudes.
Well, you'd want to change it at the inlet because these don't actually change the simulation. These just change the calculations.
Oh, this is the.
Yeah, these are reference values.
Oh,
So these are this doesn't affect the results of the simulation. It's just what values they're going to use to do some of the calculations. So you want it the same as the simulation typically, but if you wanted to change the altitude, you probably want to do it at the inlet or in the materials section. Yeah, what's up? For what?
0.0494.
Yeah, 0.0494, and that's the area of the wing. For length, the length of the aircraft 1 meter, so we can leave that, and then we can leave everything else fine. So the temperature gets defined properly, and velocity gets defined as what we define at the inlet. So that's good.
Did you define that?
That's the wing. It's the wing plan for it.
So like top view?
Yeah. So now we can go down to the next section we'll do is methods. And these are some of the ways it gets its solution. So here we have our scheme. You can do simple or coupled. Traditionally I do coupled, and that will make it compute the pressure and velocity together. If you do simple, it will calculate the pressure first and then calculate velocity. Kind of depends on what you're doing, but typically you can use coupled. Gradient, you can leave as least squared base. That's kind of how it will calculate the differences between cells, or the gradient. Pressure, you can leave second order, momentum second order, and let's do the term of viscosity at second order instead of first order. And so this is the order of accuracy the solution goes to. So you get a more precise solution with second order, but also it will make the solution more unstable and harder to converge. But since we have a simple case and simple mesh, we can do it. In a pseudo time method, we can leave that as global time step. This adds some time dependency in the calculation, but it still at the end gives you a steady state, and it adds some more accuracy.
Yeah, it's for nothing in the real world is truly steady state. Everything is a little bit of transient, but it's extremely difficult to solve transient solutions. So most things are run in a steady state format. The pseudo time step, I don't know exactly how Ansys does it. It's their own little like method that Ansys does of making their software different than other CFD softwares, where they have a pseudo time step method where they can make it so that you are running a steady state solution, but they somehow integrate a transient correction method where if there is something that is transient in the scenario you're trying to run, it'll correct for that to a certain degree. It's really complicated advanced math. I don't know how that part works, but it's really nice for, it's a nice feature that Ansys specifically will have that's better than other softwares.
All right, so now we'll go from methods to controls. And solution controls, these are time relaxation factors that you can see up here. So as you do an iteration of the calculation, you get different values, and these affect how much these values will change from iteration to iteration. So you typically will you'll run it a couple of times and you see if the solution is changing too much and you want it to kind of stop changing and calm down so you can get it converted to one value, you lower these values and it will stop changing as much. But we'll leave these as default, and then we can change them as the solution progresses.
So as Dr. Sharma said last time, the CFD is an iterative process where every single step, it runs the entire calculation and pops out a solution. That solution may not, more than often is not correct. Yeah, here's a perfect little graph here. Yeah. Each iteration is a time that it solved the entire solution for the model. However, this is basically the percent error between each one. So it'll solve it once, then it'll change the answer, change the inputs a little bit, solve it again, and it'll check to see if those two answers are different. They start out very different, and it keeps running the simulation over and over and over again, changing the values slightly to get it to where the last answer and the newest answer, the difference between them gets smaller and smaller and smaller. And when the differences in your answers gets basically near zero is when convergence happens. That's when you know there's not as many errors, when you know your answer is getting close to correct. And that's what the relaxation factors are for. Yeah?
So that's the percent error.
It's not the percent error, it's the difference between it's the error between the last value it tried and the recent value it's trying. The difference I think it's literally just a subtraction between them. It's just a difference between them. It's not a percent error calculation, it's a literal subtraction. The relaxation factors are the constant it multiplies the next value by to give it a difference to try something new. You can increase that you can increase that factor to make it try a wider variety of inputs, or you can make that factor smaller to narrow in the number of things it tries. What works will depend on how the simulation is running. Often you'll have to start and stop your simulation to see how the graphs are going. If your graphs are getting really wide bounces, you'll probably want to nail in your relaxation factors so that the bounces can kind of constrict. If your relaxation factors aren't really moving much at all and it's just staying the same number, but it's not going down to convergence, it's just being stubborn, you might want to widen your relaxation to make it bounce a bit more to have it try out lower values.
Mm-hmm. And so there's also two ways you can measure convergence. So there's residuals, which are these graphs, and so 1e to the -4 is considered loosely converged, and it's what you can use for like less where you don't need as much accuracy. And then they go up to like -5 and -6 is considered to be tightly converged. That's where, like, if you're doing a research paper, you typically want it to -6. But sometimes residuals won't converge just due to the unsteady nature of your flow if you're doing a more complicated problem.
Residual is the name of the difference between the two values.
Yeah. And then, so you can, instead of using residuals, you can also use the quantities of interest. So let's say you're trying to find the lift of this object. You can find it by, instead of looking at the residuals, you can just look at the way lift changes per value. And when it stops changing, you can Jesus, I forgot what I was saying. Can consider your solution as converged if the lift has stopped changing.
So the basic graph is the residual graph. You can tell it to produce another graph where it will do, like, for example, lift per iteration instead of residual per iteration. And if you're at the beginning, your lift value is going to go all over the place. But as the iterations continue on, your lift should begin to settle on a value. So even if your residuals are kind of going crazy and you just can't get your residuals to converge, you might still get a like semi-convergence if you look at your the value you're trying to find, like lift, drag, whatever. And if those values kind of settle after a long time, you can basically consider your simulation to be semi-converged. Because this model, the one we're doing today, is very simple. It should converge. Some models get really complicated, especially transient models, and they are very stubborn with trying to get the residuals to converge down to a proper value. So in those cases, you'll probably want to look at what plots are they called?
So report definition.
Report definition.
And so that's actually going to be the next thing we're going to define. So if you double click on report definitions, you get this screen that will pop up. You go to new. Click on that, and then you see a couple of different things. So you can find a couple of different values. You can find like volume reports, force reports, flux reports. So we're going to be using force, and let's do lift first. So click on lift, and you get this screen to pop up. So firstly, we're going to find the lift force, and so make sure it's defined in the right component. So you have your force vector, and since our aircraft is horizontal as a plane, the lift force will be acting in the y direction, so we can leave y as 1, and it's already set correctly. But sometimes, if you have your plane oriented in a different direction, you have to redo that. You got a question? So you got report definition, and then new, and then force report, and then lift.
Never trust that the initial orientation is correct.
Yeah.
Even if it might be, don't trust it because, like, say, especially if it's a geometry you didn't make, like somebody else made, and they for some reason made it where the plane is flipped upside down and the y is this way or that way. Ansys will read that and won't change it for you. So down here, always watch how your actual aircraft is oriented, or aircraft or whatever your simulator is, compared to this little XYZ plot, because that will determine what direction is lift. Because if you put lift as in the Z or in the X, it's not going to come up with anything. It'll look for a lift force in the direction you tell it, and if it doesn't make any sense, it won't pop out values that make any sense.
Yeah, and lift can be determined. I've seen in different books. Some of them will say lift only, and this is what I agree with. Lift only acts in the y direction. It doesn't, like, if you have 10 degrees, the lift doesn't act like that. Most of the time, that's called normal force. Sometimes you see that also called as lift, but traditionally, I think lift is in the y direction. So usually you can keep it as one. And then there's normal force and axial force, and that acts in the axis the aircraft oriented in. So if you have it at like 20 degrees, then that force will act in that 20-degree axis.
I imagine those are more so for like stresses on the actual structure of the aircraft, though. 'Cause
Yeah. Oh, yeah. Enough like yes. Some like especially older papers, like if you're trying to use that data, a lot of times they'll use axial and normal force instead of lift. So you might need to like convert the vectors around. But so for lift force, we're gonna select the fuselage, the wing, and the wing leading edge and trailing edge. So that's all the parts of the aircraft. So we'll get the total force produced by all of that.
Do not select the fluid. It will try to calculate the lift the air is generating on the air itself, which does not make sense. If you tell it to do that, it will try though, and it will not pump out good things.
So this is going to give us a plot after each iteration. It will show us the change in lift force. So you can change that in the frequency. We'll leave it at 1 because kind of want to see how it changes. But if you wanted to like maybe make it run slightly faster, you could do like 10, where you only see it at every 10 iterations.
That's it. This won't make the actual calculation run faster. What it does is the plot it's generating for you, it will pump out a number every single iteration. If you don't care to see it every iteration and you want to see it every 10 iterations and just wait for it to update, that's where you set that there.
You can also select print the console, and that will show instead of just the chart, you get a value every iteration. So you can actually just read the value instead of trying to figure out where it is on the
This
chart.
is the console, by the way, this section down
Yeah,
here.
we can click that just so it's easier to see. And then click OK. And so we have our first report definition. Let's also make one for drag. So we're going to do the same thing again. Click edit, go to new, go back down to force, but click drag instead. And check the components. It's in the X direction, which is the correct direction for drag.
And if you don't want to do force, but you want to do lift coefficient or drag coefficient, that's also right here.
Yeah.
We're just doing force right here.
The only thing is with the coefficients, because drag coefficient uses a different area than lift coefficient, and Fluent only lets you define one area. So I like to only use one of the coefficients. So I was going to use drag force because the area drag would use in its coefficient calculation, instead of the wing area, it would use like in this area is kind of hard to compute. I mean, I'm sure they compute. Yeah, like the frontal cross section. So yeah, let me hide this.
It's also a really hard area to.
Yeah, I mean, it was like solid
physically, because almost all of the front-facing edges of aircraft are rounded or sharp in some way. So the drag force calculation, like if you're looking at it head on and you just take a snapshot and you calculate the area of what you can see just straight head on, that's the area that it uses that the drag equation will use. Ansys doesn't actually. This is the reason why Ansys actually looks.
So I mean, you could do this in SolidWorks pretty easily. If you like had the sketch like this, you would just draw a line that follows the curves that you can see, and that will be so it's the area perpendicular to the air, because that's what influences drag. So if you want to minimize drag, you want to try to make your cross-sectional area into the air as small as possible. That's why on fighter aircraft, they have highly swept wings. So they minimize the amount of drag they experience because they're trying to fly at higher speeds. But a commercial aircraft only is slightly swept because they fly in like the transonic regime. So, but we don't need to do that now. We'll just do drag force.
Drag force doesn't, you don't need to calculate the actual
But
area for it. It'll do that way. That way you can just get the drag
Yeah.
force instead of having.
and then you could like calculate if you find the area yourself, you could just plug it into a drag force calculate, drag coefficient calculator and get it. So let's make one more. So we're gonna go to new, force report again and lift again. And now we're gonna do the lift coefficient, but this is just for the wing because the fuselage will produce some lift. It's not gonna produce much and we're using our wing area. So this will find, so just select wing, wing leading edge or wing trailing edge. So this is gonna find the lift coefficient of the wing.
You could do the total lift coefficient of the body of the aircraft if you wanted, but we're just doing it for the wing.
Mhm.
There are in aerodynamic terminologies, there is wing.
What do we select for the?
Oh, wing leading edge and wing trailing edge, or wing LE and wing T.
There's capital L lift coefficient and lowercase l lift coefficient. And those are, if it's a capital L, they are giving you the value for the entire aircraft, including the body of the aircraft. If it's a lowercase l, it's just for the wing. And it's the same thing for drag. If it's a capital D drag, it's the drag for the entire aircraft. If it's a lowercase d drag, it's typically a drag for just the wing.
All right, so now we're gonna go down to monitors, click this, so we can open it up, and you see residuals. We're gonna click on that. Yeah. It was coefficient of lift. So you go through the same and get like go through force, lift, and it's like lift coefficient instead of lift force. It's like just the wing.
Before we run the actual simulation, we should probably pause and just double check everybody has the exact same conditions.
Okay.
Yeah, you got a question?
Yeah.
Mhm.
Lift force.
Yeah.
Lift coefficient, you just select it.
Coefficient, wing, leading edge, and trailing.
Yeah.
Anything involved with the wing. Yeah.
So that's just so we capture the full geometry.
If you just put the wing on there, it would just be the top and bottom of the wing. It wouldn't include the edges. Yeah.
Yeah, I mean, it probably, I guess it would affect it some. But so now we have residuals. And so so you would traditionally set around like -4 to -6, but since we have such a small mesh count, it actually converges to that too fast and the values don't stop changing in time. So we're gonna do 1e to the -10. So you type that in,
So this is
and then
Right.
you can just copy and paste that on all.
this is setting the difference between the residuals of what you consider to be close enough to zero.
Mhm.
In most of the lab work that Andrew and I do, the typical like standard is 1e to the -6 is considered small enough or close enough to zero to be considered good enough. This thing has fully converged. This is such a simple model. It converges really fast. So -6 is actually too broad. So we need to go all the way down to -10 to get an actual good residual plot.
So we have that set, and we can leave all this stuff defined. This just is like kind of how it's saving all of the data, but it auto sets it pretty well for you. Yeah. Yeah.
All -10.
Yeah, 1 to the -10. Convergence condition. So this is something, it auto sets to all conditions are met. So that's what you normally would want it at. But also like, let's say you just wanted to converge to one of the values for some reason, you could do any condition is met and you can set which value. But we're gonna leave it as all conditions are met.
So what this means is when it will start calculating, it calculates certain values. It'll calculate the x, y, and z velocities of the air, and it'll calculate also what's called the continuity of the air. Continuity is a fancy aerodynamic term for conservation of mass. From there, and depending on your turbulence model, you might also have like a k omega that it's trying to calculate. But
Yeah, we have
sometimes the continuity is real stubborn to get to converge. It really does not like to converge. So sometimes in extreme situations where you can get all the velocities to converge, but no matter what you do, the simulation just will not converge the continuity. there you can set it to just ignore that criteria, because if you don't have it, it'll keep calculating forever until it gets it to converge. You don't want that. But for our purposes, it should be fine. The what?
No, we left that at 0.
Yeah.
Oh, mine's.
Oh, does it, wait, it's for initialization? Okay, do compute, actually, we'll go over it, and if you still have a different value at the end, then,
We'll before we actually hit run, we'll go through a quick
Yeah.
run through, make sure everybody has the same values.
So now we're all gonna go down to initialization, double click that, you get this screen that pop up. It will, start as hybrid, but, you traditionally wanna use standard. I don't know, we don't know what hybrid does, but we know what standard does. And you wanna define it as the inlet again, so far field, and that will compute the values from the inlet. Does everyone look the same? Okay, good. So this is initializing the solution. So it also gives you a chance to see AS. It will tell you if there's something wrong before you start running the full calculation and spend like a long time running that, and then you see there's a problem. And it also it gets the solution started, so it also makes it run faster at the end. So we'll click initialize, and you see in the console,
It's just
Double
kind of
select
the
the pop-up.
setup check.
yeah, it will run a couple.
Error on the initial.
Did you click initialize and it give you an error?
Um,
You can also do hybrid. Hybrid,
I don't know what it is.
yeah. That's
The
what I use a lot of times.
If you use it like once and it like
Yeah.
turned out similar.
Yeah, no, hybrid is fine. It does the right thing.
Any way I can like zoom out really quickly?
zoom out.
Yeah, zoom out of the mesh because I accidentally zoomed in a lot, I think.
Oh,
It's the,
try the one below it.
there's like a.
There's an automatic like zoom to fit model
there's a
button.
Magnifying glass and it has like a little box inside the magnifying glass. It's below
Oh,
it.
yeah, it's below the one that looks like a room. Should be,
Yeah, there you go.
there it is, yeah, you got it.
Then how do I?
Do what? Which Oh, you wanna,
Got it.
that's the.
So
low-
we'll go over a quick review while they're figuring that
Yeah,
out.
click that off,
So
and then
general, you should have pressure base, absolute,
Marketers.
and steady. Everyone good? Right?
oh, there you go.
Models, you should have spotlight or minus for viscous, and then everything else should be off. Good.
Does everybody have that so far?
Fluid, air. If you go to air, it should be constant for both. Good. And then your inlet should be, inlet, it should be a velocity inlet, and it should be defined as 71.52 with a X component of 1. Good. Your reference value should be from your inlet, and it should give you an area of this, length of 1, and a velocity of 71. Good. So then we'll go down to methods. So it should be coupled, least squared base, and then second order for all of them, and then global time step. Good. And then controls, we can leave that as default.
Should be 0.5, 0.5, 1, 1, 0.75, 1.
And then your residual should be 1 to the negative 10.
All residuals -10.
All right, so we should be good to start a calculation now. So we'll go down to run calculation, double click that, you get this. So you have a couple of things you can define, but the main thing is going to be number of iterations. So this is how many times it's going to do the calculation. Just set it at 1,000. You can like, if you wanted to like leave something running overnight or until it converges, you can just set like a really high number and we'll just keep going until it converges, but 1,000 is high enough. Reporting interval, so this is like want to report the iterations. We'll leave it at 1. If you're doing like a really large simulation, you might not want it every time because it will like take up too much data. But we'll leave it at 1 because it will be a small simulation. So now we can go down to calculate. Like that.
All right.
Yeah, no, yeah, it takes a second for the calculation to start. You see a loading screen. Your freeze, I don't know why Fluent always freeze. It freezes every time you do it, and hopefully it doesn't crash.
What was the
Crash
last?
about.
Hopefully. We can hope.
Oh,
Who needs help?
you got it.
Was that you that said that?
No,
Oh, you didn't initialize.
I said we can
Good
hope.
initiative.
Don't crash.
Good name.
Oh, wait, initialize from.
Oh, wait, no, this name. Pass it up button.
No, wait, this is
I didn't press the button at the bottom. Oh, no.
Alright, so has anyone's screen popped up like this? Have you got graphs popping up or you guys are still loading? Alright, so yeah, you should have 4 graphs. So you have your report plots you did. So this is CL, this is drag, this is lift, and then this is the residuals. You only got 3?
Oh, wait, you got it.
Oh, you got it? All right.
Yeah, the solution, this won't affect the solution. So that's okay. And you can always just get the values. So you can see how quickly it goes down. So it starts all the way up at 24, but now it's down. It's like starting to stop changing. Your residuals are coming down. So we'll see. They might actually not. I don't know what we did differently. When I ran this before, it went down a lot faster, but it's still going down really fast. It's already converged to -4, which would be fine, but we'll let it keep running for a bit.
You see, at the top line is the, oh, go back to the residuals.
Yeah, so you have your continuity.
Yeah, the top line is the.
Your nut.
Continuity line.
Your nut is what comes from the Spotlight Amaris model, and it's a measure of, what's so funny, guys? And it's a measure of your turbulence, basically. It's what the model gets, and since it's a 1 equation model, you only have 1 variable. If you're using K epsilon, you'd have 2 variables, K and ellipsilon.
Epsilon.
Epsilon, there you go. Yeah, you got a question?
Did you say that continuity was fucking, what was that?
Continuity is the conservation of mass.
So like if you have the same air, kind of air?
Well, yeah, it's also for like, it's a density related stuff. Density and volumes, but,
Of the air?
yeah, of the air. Yeah. I mean, or water, if you're doing water or whatever your fluids are. Yeah.
My calculation is failing to run. It's giving me the loading.
Is it still just loading? Maybe.
So I think that was how many ones? Yeah. So I initialized ones.
Maybe just. Well, that's like.
I mean, it's also just the fact that Ansys is a very powerful software. And sometimes your computer needs a second to run it.
Oh yeah, I think it's.
This computer just slows.
Yeah.
Yeah.
It's slow like that.
Oh, yeah. Wait,
Yeah. Yeah, let me know.
Did you say that? That all the lines are at each?
So it'll tell you. when it's-
Yeah, but for some reason, I don't. When I ran this before, it went much faster. I don't know what we set up differently. I felt like I set it up the exact same, but it's still doing just fine. -10 is like extremely low. You can see it's now to like -6. We'll let it. Let's let it run to -6 because that's like our research. That's more than enough. -4 would be sufficient, but you can see. So really, it's converged because you can see the values have stopped changing, which means the solution isn't changing anymore. So it's converged.
Well, the solution is changing. It's just changing very minutely.
That's not changing at all.
Not
But
at all.
5.1687.
I mean, that might just be the decimal value is too small for it to be reporting because it is -10.
I don't know. Yeah, but if we're within a 4 decimal value of lift, I think we're okay. All right, we're almost to -7. So we've converged to -6, which is a good convergence. So we can hit stop.
Yeah. If
If you,
question.
so yeah, you have it down in the down here. Do you have this in your console?
Yeah.
Yeah. So these are each of the values. So this is continuity. This is x. This is y velocity. This is v velocity. That's nut. And then I think this is lift because we set it to report in the console. So you can see the lift is here. And you can see lift has stopped changing. It's 5.1169. But
What does nut stand for?
It's for I don't know what it stands for, but basically there's
turbulence
each turbulence
viscosity ratio.
model has its own variables for how it judges turbulence. Splart alarmist, its value is called nut. And that's how it measures turbulence, is by measuring the nut.
See, it's fun, guys. It's funny.
Yeah.
Yeah.
I want to see how many times teams will write down the transcribed nut.
Calculation.
Reading everything you say and writing it down.
So if you guys look at your residuals, for your last value, is it the same?
Oh, by the way, okay, you hit -7. If you hit -6, if your continuity has like hit -6, go ahead and hit stop in the very bottom right.
Does 4 to the 4 e to the -7 count?
Yeah,
-7,
that's below
yeah.
-6.
Well, it's not
Wait.
1, it's 4.
Well,
Well, if
Oh.
because -7 is smaller than -6.
Yeah.
All right, so if everyone goes down here, if you see the last value it's reporting, is this the same? Because this is the lift value. It should be at least similar.
5.1.
Yeah, it's 5.1169. Well, it's actually, I guess, 51. Because it's
Oh,
e to the
yeah.
+1. So
51.1.
yeah, 0.18.
that's close enough.
Is this in pounds of force?
It's in newtons. So what does everyone have for the lift force?
It should be the value that he has highlighted right there.
What is it?
Foot. 11.5
3.
pounds.
3.
That might be the lift coefficient.
Did you set the lift
I
code?
forgot which one. I
The
know.
lift coefficient for me is 0.28. My lift force
Oh, it's the coefficient.
is 51.1687.
My coefficient is 0.28.
Okay, that's the same as mine. Yeah,
Yeah,
0.28. Okay. Well, I mean, there's slight differences, but I guess.
Yeah, these are the slight differences that happen.
And yeah, the calculation doesn't run exactly the same every time. So even if you did set it up like exactly the same, there will still be some.
This is actually why in aerodynamics in aerospace we use non-dimensional numbers a lot. We don't use meters per second, we use Mach number. We don't use lift force, we use lift coefficient. Is because, yeah, sure, you could have your plane could be going 5 meters per second in this airspeed and these conditions, but that doesn't really mean much to somebody else who's running slightly different conditions or something. That's why you want to use, like, it's fine for this reporting for now, but if you're trying to compare data to other aerodynamic engineers and stuff like that, you're going to want to eventually convert everything into non-dimensional numbers, such as your Mach number and everything.
So now we need to get data. We have our results, but we need actual data that we can use and look at.
Pause 1 second. Does everybody actually have the data?
Yeah, does everyone's solution converge?
Yeah.
Right?
Have you stopped running your program? Okay.
All right, so now we got to get data. There's quantitative and qualitative data. I remember Dr. Sharma talked a little bit about this. So quantitative is stuff you like get hard numbers from. So this could be lift and drag, or like a plot along a wing. So if you found like the pressure at every point on a wing and plotted it, then that's also quantitative. Qualitative is stuff that you can kind of look at and get a general idea, but you don't know the specific numbers. So like contours, where it's just like colored differences of pressure on the surface, that's qualitative.
Have you ever seen those like cool rainbow images of like F-16s or F-35s where you have like the green and red on different sides of the aircraft? That's a contour map. That's not actually a quantitative map. That's a qualitative of giving you the idea of what different parts of the aircraft are experiencing. They're good. They're good for showing off and getting a good general idea of things, but they're not actually quantitative.
So a good idea of a graph you guys might make if you're testing out a wing or an aircraft, it could be a coefficient of lift versus alpha, which is the angle of attack. So you can see here, the coefficient of lift gets higher and higher as you increase angle of attack until a certain point, and that's the stall angle, and then it starts to drop down afterwards. And so these are non-dimensionalized because you're using coefficient of lift and you're using Reynolds number as the two different points. You did it at 1,000,000 and 500,000. And so this would require multiple simulations at different angles of attack. But then you can plot your coefficient of lift results for each value and get this plot. So first, so we already found the lift and drag values. So now we're going to plot a pressure contour on the surface of the aircraft. So we'll go back into Fluent, and we'll scroll down to results. So this is where you can do a lot of your post-processing. There's also external software that you can use, but you can do most of it all in Fluent.
So
Post-processing, I think is what it's called, just Ansys post-processing.
I think there's also
Yeah,
Ansys.
I think so. Yeah, I've never used that, but
I don't know for contours, but also for quantitative data, you can export the values that you get from like into MATLAB or into Excel. Well, what it'll do, it'll export it as a text file, and then you take that text file and you can put it in MATLAB, put it in Excel, put it wherever you want, and you can create your graphs you want there.
all right. So if we go to Fluent, and here's the post-processing software. So if you had a this block, it's a Fluent up here. You pull this out. You can import the solution down here, and you can open up results. And this software is called.
Hey, slow down a second. Go.
We're not going to actually use this. I'll just show it, so you guys could have an idea of the other. But this software, it's a bit older, but it's got some features that aren't in it.
This is one of the other options you could use to
Yeah.
create things.
But we're just going to use Fluent for today.
Yeah.
Make a surface in Fluent, yeah. Yeah, so you can drag. So yeah, and this is also a cool thing about Workbench. You can have a bunch of simulations. So let's say we did this at 0 and I want to do at 10. You can drag out another Fluent.
Angle of attack specifically.
Yeah, 10 degrees angle of attack. And then you can just drag the solution here and it will automatically put all the stuff we did. So now we just need to go in and change the angle of the velocity, and then we can run the simulation again. We don't need to set everything back up.
Yeah.
So it makes it a lot quicker. And that's the cool thing, but you can still do it with Fluent. You can just import the file, but you can kind of have it all in one place so you can visually see it. It's kind of nice. But so now we're going to go down to results in graphics. You open this up and we'll go to contours. So we'll click on that and you get this page. There's a couple of different settings you can use. We can just leave them default for now. We'll do a contour of pressure. You can do like velocity and a bunch of other values. But pressure is good for kind of seeing the effects of the air. Then we'll do pressure coefficient because that's a non-dimensionalized number. And we'll do it over the fuselage, the wing leading edge, and the wing trailing edge. And we'll hit save and display. So now you should get this pop up. And we can analyze some things we can see. Obviously, you see this pressure of.
I want to slow down your mouse movements again because it's getting kind of choppy.
I know. I clicked this button so it auto focuses it. All right. So like if we take a view at the front of the aircraft, you can see there's a high pressure region at the nose, and that's where the air is coming in contact, and it's because you have a large surface area. So that's going to add drag, but it's kind of unavoidable because you need obviously surface of your aircraft for it to do something. So, but there's ways to minimize it. I mean, making the cross section smaller, making smoother edges, because you can see it also does it along the leading edge of the wing. You have this high pressure region, and that creates drag. But where you can see the lift being produced is here. So over the top of the wing, you see it's blue, which indicates low pressure. And if you look on the bottom, it's higher pressure. It's yellow and some orange. So when you have high pressure on the bottom, low pressure on the top, obviously the high pressure is trying to get to low pressure, which produces lift. And you also see further down the line, because also there'll be leakage at the end of the wing, is this high pressure air at the bottom is circulating around the wing and trying to get up to the top. And that creates the wingtip vortices you see. If you've ever seen like a F-22 flying, you can see those vortices sometimes if it's cloudy out.
And so if this is your wing and the air is coming at it like this, you're going to have air along the bottom that's going to be, the air on the bottom is going to be high pressure, air at the top is going to be low pressure. The high pressure is going to be looking for an area to escape to get to that low pressure zone. It's going to travel along the wing, and you'll see there'll be spillage up at the top of along it's called the wingtip, like this. That creates these wingtip vortices. That's where, if you ever see like planes fly through clouds or anything like that, you'll see these giant vortices coming off the back ends of aircraft. That's all from this one little small part on the aircraft, the little wingtips. It creates massive vortices,
Yeah.
which
Especially like, I mean, because it comes from the amount of lift being produced. Like the pressure differential, the higher the pressure differential, the stronger vortices you have. So larger wings will produce larger vortices. And so when like a 747 lands on a runway, they can't land a Cessna right after because those vortices stay there for a while and will affect the plane.
Might even
will
flip the
throw it off.
plane.
Like, I don't know if you guys have seen a video. There's a video of a helicopter landing after an aircraft and it gets just thrown around in the wingtip vortices.
Yeah.
And that's not good, I guess.
some ways that they counteract this is they use, yeah, I suppose. Some ways they counteract it is they use wing, what are they called? The
Winglets.
winglets. Where you see the wing, the very tip of the wing kind of
Yeah,
curves up
comes
a
up.
little bit. That little curve can help prevent spillage of the under high pressure air trying to get to the top low pressure, and it will cut down on the wingtip vortices, which will cut down on drag, and also make it easier for planes behind you to land.
There's also other ways you can deal with it. One of them has to do with the wing twisting. It's because it also happens due to the way lift being produced in sort of elliptical fashion along the wing. So if you can make this ellipse end before the end of the wing, that will help because the vortice will form here, and then it will just get blocked by the wing.
Yeah.
So that helps minimize it as well.
So like the lift generation, if you can imagine it as like a force going over it.
Yeah.
When the ellipse typically ends right at the wingtip because that's where the wing ends, and that's where the force is going to end. And that when it ends right there, that's where the vortexes will try to travel and reach to the top. If you can make that dome of force end before the tip of the wing, due to twist, the vortexes will not be able to go over to the top because they'll be trying to form underneath the wing, and they'll be blocked.
All right.
Little design there.
Yeah. So that's kind of what I'm trying to implement in this course because I know a lot of you guys are working on competition teams. So kind of want to show the reasons, or if you ever get into it, like, I mean, because we run the CFD and you get the results. If you don't know what they mean, it really doesn't mean anything if you don't know what to change about the aircraft.
Yeah.
So the next thing we're going to do is plot some streamlines. And this will actually help visualize the vortices. They won't be extremely strong because we're flying at 0 degrees angle of attack. So there's not a large pressure differential. And also at high AOA, you get a stronger vortice because there's a larger pressure differential producing more lift. So we'll go down here to path lines. Yeah, and you get this screen that will pop up. So there's some things you can do. I'll define it starting from the wing trailing edge. So this is where the path lines will start from. And then we'll do color by, do velocity. So that will color them by velocity so we can see the change in velocity as it goes over the wing. We'll click save and display. Okay, so you get this.
Let me just close that window.
Yeah. It looks different than when I did it before. It's only doing over the top edge of the wing for some reason. Let me do this. Collect fuselage, see what that looks like. I just when I still did this earlier. And now we can see the fuse, but it's still not showing the bottom contour. We select, oh wait, I select trailing edge instead of leading edge. That's why. It's starting from the back of the plane, so that's why it's showing that. So select fuselage and wing leading edge, wing LE, and this will show up better. Yeah, here we go. So now these are velocity contours, or velocity path lines. So it's basically a path a particle will follow. So we have it at 500, so that's 500 of these. You can do it more fine, but it uses a lot of the computer because it's kind of complicated for display. So
500 or what?
So
500 different lines.
So each line is it picks a line of the air and it tracks the air as it goes across the aircraft. That's why you can see it going all the way so far behind the aircraft. You can increase the number of those lines or decrease the number of those lines. Be careful when you're increasing them because it will kill your computer.
Jesus.
You can see like.
Yeah, here, and you can even see. So you see a small vortice.
It's like tiny, but
It's hard to
Yeah.
like. I hate Ansys.
Like Andrew said, the wingtip vortices for this aircraft are going to be kind of small because it's it's not that big of an aircraft and we're running at zero angle of attack at kind of a slow speed.
But yeah, and if you see the wake of the wing though, you can see the like circular, because lift is generated in a circular fashion. So you can see how it kind of, you see that little curve at the end because it's trying to form. You could, here's a better view. There we go. You can kind of see the vortice forming here, but it's just so small and doesn't wrap around until way back.
Yeah.
But and also as it gets stronger, the frequency of the vortice gets smaller. So you see it wrap around multiple times. You get that effect. And then another thing to look for is interference, drag. So that's when you have two structures interacting with each other. So if you have a wing and a fuselage connected, the flows on those two will interact and will interfere with each other and cause drag. So you can see here, you can see how the wing is kind of messing with the airflow of the fuselage. That will add some drag. Ways to minimize this is like making a fillet from the wing to the fuselage to smooth it out, the transition between. There's other ways. There's wing fences, which they use in between wing planforms, and that's a way to keep the flow straight and like, because sometimes, because you can see, well, this one doesn't have different sections, but some wings will have different sections. Like one will be curved at this angle, one will be curved at this angle, one will be curved at that angle, and the flows from those different sections can interact with each other. So they have a fence run along the wing to prevent the flows from interacting, and that minimizes interference drag. Because there's two types of drag. There's parasite drag, which happens at zero angle of attack. And so that comes from surface friction, just the pressure differential from like the high pressure where it hits the nose, and then interference drag. And then there's induced drag, which is drag that's from lift. And so because you get that pressure differential, but it's also acting in the X direction if you had an angle of attack. So lift also adds drag when you produce it, and that's just kind of an undeniable fact that you can't get around. So
a little bit of a paradox because in order to have lift, you need induced drag, but induced drag saps away the energy from the lift, so you have less lift. So it's a weird little paradoxical balance act with aircraft design where you want to minimize induced drag as much as you can to get more efficient lift, but if you completely get rid of induced drag, you can't fly.
and then another way to visualize the flow around the aircraft would be using contours on a plane. So I'll show you quickly how to add a plane. So if you go to surfaces, you get this pop. Well, actually, no. So close this. Actually, right click on surfaces, and then you see new pop up, and you go to new, and you go to plane. You select that. And now we can make a new plane. So you can have it defined. We'll define it on the XY, so we get horizontal cross section. So go to XY plane, and you can see it forms all the way. Well, it forms kind of down the middle. So if the aircraft, I believe the wingspan was like 0.4 meters, or the half wingspan.
So what he's doing here is, if you wanted to, for example, analyze like the cross section of a certain part of the wing, you can't really do that by itself without creating a sliced plane through that cross section. So you can go to right-click surfaces, insert plane, do the different axis you want the plane on, and then you can do the Z to offset however far out from the central axis you want your cross section.
So
to
if
be.
you want to like see the flow at different points on the wing. So let's do
Exactly.
do 0.1 meters for Z, and you can see it forms a plane that cuts through the wing right there. And we'll create that, and then we'll go back down to contours. We'll make a new one. You make it on the plane you just defined. I don't know why there's two. And let's do pressure again.
So then it clicks, you're chopping up a lot.
So we have pressure coefficient, and you define it on the plane you made. It will say plane and some number. Hit save and display, and then you get a plane. It's display. Oh, it's because it's still displaying this. Okay, there we go. So now this is a cross section of the flow. So it's just an airfoil, but it helps you visualize the flow at different spots. So I mean, you can see here, you can see the same instances where the drag is produced because it's high pressure. You can see the low pressure on the top. And then if you wanted to like visualize the flow of the fuselage, you
So
could do.
one thing you can do to make this kind of visually better is if you go into, right now, you see how it says global range is selected? That means that it is using the global range of like what is the lowest pressure to the highest pressure on the entire aircraft, which is kind of hard to see. And that's why everything kind of just looks green right now. Because comparatively to the lowest pressure, everything's green. If you click on, if you undo one of those, yeah, there you go, undo auto range, you can then set whatever your minimum and maximum pressure is, and that might give you a better visual contour of what's happening.
Yeah, so set this to -0.8, and we'll set the maximum to 6.
Yeah, do 6.
Well, no, 60. Wait, no, 0.6. Yeah, 60 would be a really high pressure coefficient. You don't normally see it over.
That thing has a weird hump on it now.
Yeah, contour object is now valid to display. Oh wait, I don't have a plane select. Oh yeah. Oh, I think that's probably because it's either too low. It's probably too low. So we need to move our minimum down. Let's move that to like
Yeah.
-1.
That means that the pressure right there over the wing is too small for your scale. So there you go. Now you adjust the scale a bit more. Now like, zoom in a little more so you see
Now
it.
you can kind of see the picture better.
Yeah, now you can see that there is a very visible low pressure zone on the top. That is how the lift is generated. Sometimes your visuals are what's going to screw you over in Ansys. You could be getting correct results but everything just looks green. I can't tell what's going on. It's all green. So going in and editing your scales can give you a better showcase of the color contours to give you a better idea of what's going on.
And then one last thing I want you guys to see is, all right, so deselect the plane you have and select symmetry. This will show the flow at the center, and so it's the flow of the fuselage, basically. So you can see the cross-section of the fuselage, and this can help you make design decisions about fuselage. So you can see high pressure. So, I mean, ways to minimize that would be, I mean, making it more rounded, I guess, but it's already pretty rounded.
We'll make it more sharp.
Yeah.
But
then you can have, also, because sharp edges, so here. Well, you can't really visualize. So, because it's such a small one, which is good, you want to minimize like drop-offs like this. That's why they have it like filleted up all the way here instead of just making it a sharp stick. If you had it just sharp like this, you can see.
So if you zoom
If you
in
would have cut it,
if you zoom in on it, I can point it out. So normally, if you have a sharp edge like this, the air will traveling over this and up along this. There would be a gap right here that would be a vacuum. That vacuum would be sucking air from behind the plane forward, which is the opposite direction of travel, which means you're going to get a big drag value there as your plane is literally sucking itself backwards due to these sharp.
yeah, you can actually kind of see it in the like you can see how the
see
flow
that?
separates here, and then you get a little like vortex region. And so this is an area.
This is really bad.
Yeah, because you don't want low pressure on the back because that kind of acts as the same as high pressure on the front. That's pulling it the wrong direction. Well, it's pulling it backwards because it isn't trying to pull. So you want to minimize low pressure in the back and minimize high pressure in the front.
And analyzing the shape of your fuselage is very important because your wing is not the only thing that generates lift. It's the most important thing for generating lift, but the fuselage and the shape of the fuselage can aid into lift generation or really aid into drag. And this is where all the different things for drag comes in. Sharp cutoff like that will do drag really terribly. Yeah, perfect.
Yeah, this shows a bit better. Now you can actually see the fuselage.
This whole area is a vacuum that is sucking this plane backwards.
I mean, and so they minimized it by making it small.
Yeah.
So you can see it's really not, I mean, because at some point you have to have a drop off.
At some
So
point,
you want to minimize it, but you can see they did a smooth edge so the flow doesn't separate. Because flow can follow a smooth edge without like losing energy and falling off. But when you have a sharp drop off like that, the flow can't stay separated, and that's what flow separation is.
I'm stressing that this is really bad, but due to how well swept up this is, compared to the entire aircraft, it's actually not that bad. But if that area, that truncated area was any bigger, it would be creating a larger and larger vacuum suction at the back of the plane.
Yeah, here you can actually kind of see the wingtip vortice. I mean, it's very small, but you can see there's a couple strands slipping from the bottom and going up to the top.
Yeah, right here. These ones that are slipping, they're kind of going.
And you can see the
the-
vortex kind
The
of.
overall direction is still this way, but they're slipping upwards.
Mhm. All right, well, I guess any questions or remarks?
Alright,
This
is crazy.
It's
Huh?
crazy, dude.
Crazy. Yeah,
Oh,
aircraft design
That
is
was
crazy.
So that's kind of all for now. So for day 3, since we finished this one, I kind of want to. You got a question? Someone say okay. Unsteady.
Let's say what?
Okay, yeah, that's transient. Okay.
Transient.
So yeah, these are some of the stuff we could do next week. We could do internal flows, which is kind of like the flow inside an engine, or pipes. Supersonic. I was thinking for supersonic, we could probably do a rocket simulation because I know there's some people from rocketry, and I don't want to just do aircraft. Yeah.
We do like an FSAE simulation. I'm sure.
Oh, for like a car,
Was that?
like the Formula One.
No, not Formula One. Formula SAE.
Okay, yeah. Yeah, we could. I haven't really done. I wouldn't know how to mesh the car.
I don't know how to mesh cars. Do you? No, I said I don't.
No.
We're both aircraft guys.
You got both.
We could maybe. Are you on the SAE team? Yeah.
Yeah.
Okay.
Uh,
I know.
I mean, we
They-
could.
What's the
Structure
guy's-
loves cars.
Has he? Oh, he does.
Yeah, ironically he's a huge car guy. Yeah, he's like we'll talk your ear off. It's really funny because it doesn't seem like a car guy. But
This guy.
huh? What?
Okay. No.
Oh,
All right. Supersonic. So we
he
can
probably
do.
knows how to do it essentially.
Yeah.
We could ask him.
I mean, we could figure it out. There's actually on Ansys, on like their website, they have tutorials like for SAE since it's such a big thing. If you look up Ansys,
What's
that?
Watch the.
You watch those tutorials?
But
And then
everybody has a different approach to meshing, it seems. Like there's so many different ways.
do you guys use Star CCM?
Yeah.
Yeah. So I mean, so it's Star CCM. I haven't used Star CCM before, so I wouldn't know.
This is the star CCM guy right here.
This is Star
And
CCM.
like holds your hand.
Oh yeah, yeah. I know it's more of like
You
a
have to look for it.
yeah. Fluent's kind of like the most commercialized, I think, out of all of them.
I mean, I think the most handheld commercialized one is simply SolidWorks for fluid flow.
Yeah, but they don't really do proper fluid.
I
It's
mean,
kind of just, yeah. So I mean, maybe we could talk maybe with and having SAE hold one themselves. I don't know.
yeah,
I think it's Nathan, right? Who's over aerodynamics.
Well, so he doesn't know how to do
He does it.
it. The dude who taught me fucking graduated. So
Oh,
yeah.
and you didn't leave anything behind?
Nathan.
Dang.
Yeah, so I don't yeah.
That's
Well, no, he did, but
That's fair. So that's one idea. Well, let's start writing these ideas down.
Okay, so yeah, I can add FSAE.
Yeah, so there is moving mesh where for propellers and
Yeah,
stuff.
so this would be, so it's called turbo machinery. So it'd be like simulating a turbine or propellers or anything that spins like what are they called? The wind things?
Oh, the auto gyros?
No, the wind farms.
Oh,
Wind
wind
turbine.
turbine.
Wind turbines, yeah. That's actually kind of a big thing. There's a lot of jobs for that because they're building a lot of new wind turbines. They need them to be simulated so they can figure out the optimal place and blade size so they produce the most energy. So that's moving mesh and FSAE car. So how is that really different from what we did though? Because that's still going to be incompressible flow, like the car simulator. Because that's kind of the same as what we did. Because it's still low speed flow.
the only issue that I I've gone before, but it's really just presented in that.
Yeah, and I don't know if I could really help you with that because I don't know anything about size. So I don't know if it'd really be helpful
Yeah.
for you.
Well, this has been helpful in and of itself. I
Yeah.
just trying to figure out how I can mesh. It's not there's a lot of different areas that have to be meshed.
Yeah, because I get the class so much. Yeah, I haven't.
It's got a weird geometry.
Yeah, I wouldn't be much help with that. I haven't
I
done
imagine,
something that complex.
imagine you could try simplifying the geometries maybe to get rough ideas.
Yeah, but I think they kind of, because you need to simulate a car and a wing.
Yeah.
But if you want like, if you want more exact models, so that's something you can compare the difficulty.
Yeah,
No, we have a very,
Yeah,
simple CFD running model.
but it's just this. There's still even with that. There's so many edges and faces you have to figure out. Yeah, I don't know if that might just be as
Yeah, all good.
that's difficult to do.
I mean, I recommend unstructured mesh and using inflation layers. Because with all those sharp angles, it'd be hard to get a good structured mesh on that. They're gonna fold a lot. So unstructured meshes and wherever you can, like maybe especially like with a spoiler or whatever at the front wing, get inflation layers going on those.
Yeah.
Okay. Beyond that, I don't know the geometry ratios are.
Yeah, okay.
Those are the ideas that come to my mind.
Yeah. Are you guys trying to do an unstructured mesh right now, or is it been
Well,
structured?
so we have, Star and Luke over here, he's good with Star CCM.
Yeah.
But we're trying to figure out Ansys as well, have that as a backup.
Yeah.
So we're not in a particular rush, but I'm just trying to figure
Yeah.
out.
I mean, yeah, you can maybe try it in Ansys and see if that's easier.
I
Yeah.
know in Fluent, there's like display, or like there's the curvature thing that you could do with it. And it like gets it really tight with the curvature.
Okay.
Yeah.
But it also makes like a ton of cells.
Yeah, so you're gonna have.
So you gotta be really like careful with it.
Do you guys have like a computer or something you guys run it on there?
Yeah.
Yeah, I don't know. I mean, yeah, so you just need to figure out kind of what's the limit of that computer. Yeah.
Has
Eight.
Oh,
It
okay.
has 32 gigs.
Okay. I mean, that's,
More.
yeah. Ooh, that's okay. I mean, that's good enough to run stuff.
I mean, yeah, it's gonna have to run stuff like run with other stuff they're counted on.
Yeah.
I'll run on one of these computers. And I'll-
And
Is this room stay unlocked?
no, this room is not staying unlocked.
Yeah, that'd be nice if they made this room. 'Cause this is the only room that has Ansys.
Yeah.
I mean, that's all right.
I didn't even know it
So
existed
like,
until
if you're trying to
before
run
this
a
show.
better mesh, that might get even slower. It might be nice.
It's not good.
Yeah. I don't know, because this room stays locked.
No access for students.
I mean, you
Yeah,
can book,
unless you're
you can
taking-
book the room, like your club can book this room themselves.
But you gotta like book it a week ahead.
So, yeah,
Really?
So, yeah.
yeah.
It's like, it's not as simple as the other rooms. I mean, Ken can attest to that. He's the one who handled the booking.
2 weeks.
Yeah, 2 weeks ahead, actually. So it's not something that I think, because, yeah, they have a class, I believe it's called CAE. What's that class called?
CAE?
Yeah, where they do.
Yeah.
So there's one professor, I think, that teaches Ansys. All the other ones do SolidWorks. I think he uses this room.
He said he was gonna teach, I'm taking this class right now. He said he was gonna teach Ansys, and then halfway through the semester, he was like, ha, JK, not teaching.
So I guess
Ansys."
no one's using this for
No
Ansys.
one's teaching.
I've seen people in here before, so they must still use this for
Yeah,
the
no
class.
one-
They probably just don't
No
use
one's
Ansys.
teaching Ansys. Which is why, I don't know, it's like one of the most popular, usually used, like, it's even in industry and research, it's used.
Aren't they other computers on here because of Chakosky's like CFD class or something?
Yeah,
Yeah,
I
well,
guess
like,
he's just not using them though. I guess you got it. At least you got it downloaded. We can use it.
let's see it.
Yeah.
I actually, real quick, before you go, there's something I wanted to announce before people. So, besides just, part 3 of this and what we're gonna do next part, there is a project that AIAA is putting on that, AIAA in combination with, SPS, Student, Physics Society, called the CANSAT project. It is really cool, you know about it, where we are competing with other like schools and everything and organizations around the world to build a satellite and launch it. Design, build, and launch a actual like little CANSAT satellite. It won't go up all the way into space, I don't think. It'll go up into like the high stratosphere and then come back down. But we're looking for members. I'm extending this is an inter-club thing, by the way. It's not just an AIAA thing. We're working with SPS, AIAA. We've talked with ARCT a little bit about it, a little bit with rocketry. but the word hasn't gotten that far out yet. There are a limited number of seats. There are only 10 people can be in the team. There's currently like 4 slots basically filled so far. But we haven't heard much from besides those 4 people. And we need those slots filled, and the due date for like applying is November 1st. To give a like better idea of it, November 1st is the due date for like team roster, team name. February 7th, I believe, is the due date for the like proposal of the satellite, and it's going to be launched in June. It's a great opportunity. It'll be it's inter-club. You'll meet more people, more disciplines around the school. You'll get your name better out there. You'll build something and launch it. It's a great opportunity. You'll be using softwares like this, doing trade studies and stuff. Yeah. Anybody interested so far? First, well, first I'm seeing who's interested. Yeah. You're interested? You're interested? All right, cool.
Didn't I already sign up?
Yeah, you did, but I got your email now finally. Yeah, I know you're
Can I
interested.
use my Gmail?
Did you put your Gmail? I hope not. Please don't ever use your Gmail. Yeah, no, you put your student stuff. Okay, cool. So let me get more stuff in here. So those who raise their hands, what is your name? Matthew. I'm gonna put a star by your name.